let's not. Let's cut it off.
Right.
Week 8. I'm gonna explain briefly some of 3 items, but it's all just touching it. Because actually this you can go on forever, this one you can go on forever, this one you can go on forever, so I'm just gonna touch some subjects, and it's not final. Yeah? Any idea what it means? No, right? Yeah, vision, it's probably pretty clear. Vision, language, reinforcement, and I'll start with this one. Does anybody play Go? I did it. Yeah, do you play Go?
It seems to be a game which name was Othello.
No, that's different.
Oh.
That's with the switching. No, it's a totally different game. I played it when I was young. In Asia, it's a big game. It's much bigger than chess, and it's considered the most difficult game in the world. And the reason is, especially for computers, the reason is that it's got 2 to the 10 to the 170 possible legal positions. That's more atoms than the universe, than the visible universe. This number is not a little bit big, it's huge. So there's a lot of different possible combinations of how those stones can sit on the board. So not the easiest game. And this is the game people thought, well, it's probably never gonna succeed with computers, basically. And it did. And this is a newspaper. This is a still from a movie. I've seen this movie like a year ago. It's super interesting. I really think you should see it. This is a team from AlphaZero, AlphaGo, and they beat the world champion Go player. And this was world news in Korea, in Japan, and China, etc. So this is really the front page of the newspaper, and this is the team of the programmers. So it's a big thing. They managed to win it. It's nice to have a look at this documentary. And I'm going to take a side step to chess. And not because chess is so interesting, but we'll see later on. So chess, computers playing chess started in 1956, and it could play the level of a child. Then some other, a little bit later, it had a rating of 1529. Anybody know his chess rating?
800 or something.
So these are chess ratings, right? Yeah, I'm probably the same level, but this is like the current world champion, 2700. And you see that slowly they get closer to the ratings, and I think Johan still remembers this. It was a big thing at the time. This was the first time a human world champion was defeated by a computer. So that was pretty cool. And development of those chess programs continued. Stockfish in 2017 had a rating of this. So way of the scale, right? No human will ever be able to beat Stockfish. This program, there was a lot of man hours put into it. Because there were a lot of chess grandmasters helping the computer getting better. So that's basically, what kind of learning is that? Supervised and supervised? Supervised. And supervised, right? And it was not with machine learning or something, it was some kind of knowledge model, whatever. And then AlphaZero, the same program which learned Go, it played, they said, these are the rules of chess. It played one day a couple of games to itself, and it beat the crap out of Stockfish in one day. No input from humans whatsoever, and it beat the crap out of Stockfish. Where like there were really more than 1 million hours of development from humans. So when I read this, I was kind of shocked. It was 2017, and I was given already vision at the time, so I was interested in stuff. But this was kind of like, whoa, kind of scary. You agree? It's pretty amazing, right? In one day, and it beats everything in the world. So we want to look at why. How does this work? And the key is reinforcement. That's the first topic. So this is the intro why this is an interesting field. So this is some visual depiction of the program or the neural network of AlphaGo or AlphaZero. There's different types. First you had AlphaGo, and then they said, well, I can play all games, and then they called it AlphaZero. But there was also really a little bit improvement again. What do you think? Where does it look like? And remember all the things Johan explained already.
Like a neural network.
Yeah, and what kind? It's already written. This, you remember a little bit from Johan's pictures, right? It's a CNN.
CNN.
Yeah, so not that exciting in itself, right? But there's a big difference for reinforcement learning. Because in the case, do we have the labels? Do we know the best moves? Well, yeah, that's a little bit complicated, right?
Yeah.
It's a little bit, we could ask a grandmaster, that's true. But then we need to have the labels for all the different possible games. It's kind of tricky, right? So basically we don't have the labels. This is the case for reinforcement labels. We don't, reinforcement learning, we don't have the labels. So we don't know for each input what's the correct output, basically. So that makes it straight away much more difficult. And what I just said that, well, basically AlphaGo is a CNN. The interesting stuff is around it, basically. So how do we do this? Any idea?
Maybe by the game, it continues to work by the network, and then there would be a final output.
Yeah.
You can compare all the outputs to see if they are appropriate or not, and then use them as the input again.
Yeah, basically, yeah. So what you've got, basically, you've got the thing you want to learn, and then it gives an output, and then you need something to know if it's good or not, right? So what do you need to do here?
It plays against the
Yeah,
system, right?
here you need to play the game. If I want to do reinforcement learning to ride the bike, what do I need to do here? Ride the bike, right?
So it's basically a bit of trial and error reinforcement learning.
Yeah, a lot. Yeah, a lot. Yeah. But the extra stuff is basically, right? Because you play a move or you put some input in the real system, and then basically that's the output for the next step, right? I'm going to show you some examples. This is a really simple one. This one was still from Willow Sheets. And you also see already the disadvantage also of reinforcement learning in the physical world. What do you, are you bored already or not? A little bit maybe?
Takes time.
It takes time, eh? If you want to do it in the real physical world, it takes a lot of time. Okay? There's some way to speed it up. That's what this one I will play a little bit longer. Here they used some ways to speed it up. This is actually with noise.
Wel lullig dat niemand even komt helpen.
Ja.
It's gonna get worse. It's gonna get worse. They're not gonna help them, they're gonna make it worse. And this is actually what they did there. They really used some clever stuff, because normally you cannot walk in 30 minutes, right? Where do you have to compare this with? When you look at humans, where do you have to compare this with? Huh?
Baby.
Baby? Yeah, it's a baby. It's a baby learning to walk. it even, have you seen like a veulentje?
Small horse.
A small horse, it's just a boring horse. It kind of looks the same thing, right? And that's no coincidence, because it's actually the same thing which happens in our brain. How long do you take about learning an exam? How much time does it take you? Couple of hours, couple of days? Yeah? Is that supervised learning or unsupervised? Yeah, you know the answers, right? How long does a baby take to walk?
A year or
Yeah, it's much more difficult. Oh yeah, this is what I told you about, he's not really helping me. So this is actually quite difficult, right? It's really different things. Nope, now I'm stuck in YouTube. Yeah. So we want to know which action to take in a particular situation. And what is the tricky thing in this case? I don't have direct feedback, right? I don't know if, well, I'll show you. It can be used for a lot of stuff. Games, robotics, traffic control, decision making, etc. And you can do basically two things. You can make a safe environment in real life, physical, right? Or you can do it in a simulated environment. But we saw with the robot, which worked in 1 hour, which is normally way too quick, they used both systems. So what they did in a simulated environment, they checked which was the best move, they let the robot make that move, and then saw the difference between the simulated environment and the reality, and then they adapted the simulated environment. So it was actually a really smart model, but okay. This is much quicker, right? You cannot do in real life 1 million games of chess in 1 day, but in a computer it's possible. So hopefully you can do something like this, but it's not always possible, and you can do mixed hybrids. So it's not supervised learning, you don't know the labels, but it's also not unsupervised learning, right? It's a little bit of a mixture. You're trying to find out the labels, but you don't have a direct process to do that. So it's in between. Yeah, the idea is to use a carrot. Okay? Like, hey, this is the right direction. So we're working with rewards. But that's actually quite difficult. I'll just follow the sheet. So basically what we have is some controller, that was this part. This is the thing we want to train. We have a process, that was this part, simulation of chess or simulation of a moving robot or whatever. And we have some kind of feedback mechanism to make sure that this one learns the correct behavior. But this one is actually quite nasty, there's some nasty stuff in it. I'll show you, the solution, when you have something which works, we call it a policy. I'm missing one slide. Well, I think it's in a different order. Let's say, if we do go, I'm gonna check that slide because I want to show it now. Where's the slide? No, okay. If you have a bike and you want to drive it, if I do one movement, how do I know if it's good or bad? The problem is, it depends on the moves thereafter, right? So it's difficult to evaluate the result of one action. If I play if I play chess and I make one move, how do I know if it's the correct move? I cannot do that only on that one move, and I have to look in the future, right? That makes it really difficult. It makes it really difficult because we have all those different rewards over time. And how do we handle that? How do we say, well, in hindsight, that one move was actually that good. So that's large part of what they do. First, I'm going to show you an example, and first we're going to do this. Now, I'm probably really bad at it. Yes, I'm trying to balance the stick with a card, right? Now, first I'm going to apply a really stupid policy. This problem, by the way, it's already solved analytically. I'm teaching control theory in electrical engineering, and then we play for 5 EC, and then we get close to doing things like this. So for this problem it's actually not so useful because it's solved already, but it shows the idea. So first a really stupid policy. And I'm going too quickly, sorry. How do we do the process? There's a lot of different ways. In Python you can import gym. You have to install it also when you're in Spider. If you do it CodeEmp, then you can install it online, blah blah blah. But what you can do is basically you have a free simulation model. So that's nice, right? We don't have to build it. And then the controller part, we're going to do a really stupid one. From the process, what we get back is the state X. And the state X is, well, what's the status of that system? And one of the states is the angle of this rod. And what we're going to say is that if the angle is like this, then you have to accelerate this way. If the angle is like this, you have to accelerate this way. It's not so intelligent, right? Do you have any idea what's going to happen?
It's going to accelerate too quickly.
To one side.
It's going to want to fix itself and shoot away.
Yeah, close. Okay. This is an example of such a policy. And this is also, this example is in the book actually, and it's also online. So you can play around with this yourself, it's pretty cool. What's happening, and the graph is a little bit more clear, is this. And it stops at the end, but that's because the angle was too big. And when the angle is too big, he says, hey, you're beep, end of game. So what's happening? So here you see the angle, here you see the acceleration, so it's the speed actually. So here you see its acceleration this side, and then the other side, this side. And what you see, it gets more and more unstable, right? Logic? Mm-hmm. Yeah. Okay. Then we're going to try this kind of network. And there's actually a little bit more to it, but I'm not going to explain everything. It will take too long. We're going to use a little bit more observations. We don't only use the angle, we also use the position of the card, and we also use the speed of the angle, so the rate of change, and also the speed of the card. So that's 1, 2, 3, 4 are different physical constants. Basically, we've got just a neural network with which kind of activation function you think when you look at this? If you're smart, you're looking here, but that's the same, right? That was the baby, right? It was here fixed and then it was linear. And at the end it's a sigmoid, this one. Right? Just a side step, why didn't we want to have here just linear stuff and also here just linear stuff? You remember, Johan explained?
For the error correction?
No? If it was all linear, then it also could only solve linear problems. Right? If your problem was non-linear, you had to have some non-linearity in the model. That's
Sure.
correct, yeah?
Yep.
Okay. And we're going to try it again, and we're not going to train it. Not yet. So we're just going to see what happens. Chaos, right? Well, it's not trained, so what did you expect? So this is the graph, and it's just doing some kind of random stuff. Okay, now we're gonna try to train it. Oh yeah, was this better or worse than the original?
Worse probably.
Yeah, you have to look at this axis, and you see that it's here it's longer stable than here. So it's worse. And then we train it with reinforcement learning, and then it does this. And the nasty thing is, if it's out of bound, then it also says the game is over. It's, but it keeps it stable. My computer, all the stuff we did with neural networks up to now, did it take a long time for your computers and stuff like that?
No. Yeah, depending on the epochs.
Yeah, okay, but basically no, eh?
No.
This is awful, this kind of stuff. This is really like, I tried to run the whole code, which is also in this is like halfway the code, and afterwards he did all kind of optimizations, and I didn't yet manage to finish it in one night. So it's quite awful to learn.
Did you run GPU on CodeEmp?
No, I couldn't run it on Colab.
Right.
Because I don't have a credit card, so I can't buy the unit. And this one doesn't have a GPU.
Okay.
So
Why is this such a difficult problem for the neural network to solve then?
because for each action, it's not like is it good or bad. No, you have to do a whole simulation process also.
Oh, yeah.
So there's an extra step basically, right? It's a lot more work.
So does it, with the chess game, play one move and then play the entire game out and then check, okay, was this one move?
Multiple entire games. We'll talk about it,
Yeah.
but not all possibilities.
But you can never say after a game, okay, this one move was good or bad, right?
That's exactly the problem. That's exactly what you now say is exactly the problem of reinforcement learning. How do you do that? That's the difficulty. That's the difficulty. And I'm going to explain a little bit more about it, but that's still where we're struggling. Okay. Well, now you can see 140. So it's much more stable. And I think if we also would have, one way or another, put some kind of restriction that we didn't want to, if we put this in the reward system as well, that it should stay in the same area, then probably this thing was also solved. Just some side. Supervised learning, that's what you did until now, that wants to work, wants to learn. Reinforcement learning, you really have to force it to learn. And if you do something wrong, then it's not going to work. So it's really much more difficult. And this is exactly the problem what you said. Is this a good move? And this is like, depends on all the next move, there's almost infinite number of next moves. So how are you going to fix it? And this is also true for something like this. So how are you going to fix it? Well, one first way, what they thought of, is that if you look at your current reward, maybe you can have some kind of metric how good the game is playing, how good this move was, but you also look at the future rewards, but you discount each future step. So let's say I made a brilliant move, and the reward for that game, for that, what is it?
Z?
A
move.
A move, yeah. The reward for that game was 10.
Sorry.
And afterwards I make another move, it was also 10, and another one is also 10. I could have a discount factor, that let's say the discount factor is 90%. Then my reward for this is 90 times 90 is 81, so this is 8. So because basically it could also be that this is a worse move, right? It's not fair to have all the success of the next move only attributed to the first move. So that's one of the ideas. It's one of the big ideas. And it's also got an advantage, so we don't have to play the game until the end. We can do already a little bit with this move. And here's an example. Let's say I've got that stick, and I'm doing left, left, right, right, left, right, 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 right. This is what I did, and I want to know what is the reward for this one. And my reward function is 1 minus absolute degrees divided by 90. So if the pole is like this, it's 1, my reward. If the pole is like this, it's 0. Right? That seems, I just made it up, seems like a not too bad idea. And what you see is that, so in the beginning left, it was minus 20 and left, so here it's getting better, right? Apparently I made my the coordinate system in such a way that if it's left, then the angle is minus, then I need to move left. Is that true? Yeah, it's true. So it's get better, here it gets worse again, worse, worse, worse. So these rewards is what you see, right? These are the discounted rewards. So here the factor is still 1. What's my discount factor? 95%. So here I'm only taking 95%. Here I'm taking 95 times 95 times this number. Here I'm taking 95 times 95 times 95 times this number. And you see that you get less and less reward. And then I just sum it and I've got my reward. But what is the problem? So this is the example, but it could also be, I could do left, left, right, right, left, right, right, right. But I also need to check basically, but that's a different simulation, right? It's a different simulation. I could also do something like this. What you see already is that the reward changes. Apparently the guy after the first move was smarter, so then he's saying, well, now maybe your move was not so bad. Or it could be that the guy after me is really stupid after the first move, and then it's lower. So that's the problem, eh? What are we going to do with this? And this is a deterministic system. I don't know. Do you know what a deterministic system is? If I know all the inputs, I can predict all the outputs in principle perfectly, right? But there's also systems where there's a little bit of chance involved. In reality, for instance, when you walk, well, this seems like a good idea, but sometimes there's some stuff underneath it, and I'm going to do something like this. So, okay. But even with a deterministic system, we can see that the amount of possibilities is really big. And now I'm going to show you something scary. This is one way to get out of it, and I'm not going to explain it. I'm going to translate it to this. That's a little bit more reasonable. And I'm going to now explain it. So I'm not going to explain this one, I'm going to explain this one, which is more or less the same. So we have an action, A, we have a state, that's the angle, and we have a reward, R. Right? So basically what this says, there's some kind of Q value, and the Q value is kind of like a accumulated reward or something, or like the quality function or the reward function, whatever. So we say that the new Q value for an action A and a state S is given by the reward of the next state times the chance of reaching that state. Yeah, okay, in this case it's deterministic, so this one is always 1 or it's totally fixed, that's always 1 actually. But in reality, if there's some kind of chance involved, this one gets interesting. Plus max discounted future Q values. So what you're basically going to do here, you're going to look at, we had 3 different possibilities, right? This one and this one. What it basically says, take this one. This one was the biggest you had until now. So that's the new idea. Yeah, you're gonna, okay. And then the next step for your next simulation, you're gonna try to pick the action with the highest Q. Because that is probably the best move, right? And then you run it again and see if it changes. And this is an iterative process. So each time you run the simulation, you don't throw away your old information. And it could be that it's not valid anymore. If a new move is better, then it could be that all the old moves are, there's a possibility for the old moves to be better as well. So it does change it, but it doesn't throw it away. It doesn't start with 0. Yeah? This is one of the basic ideas of reinforcement learning, and there's a lot more to tell about it. There's a difficulty a little bit. Okay. So what you could just say, I'm going to update it like this, right? So this is basically what I just explained. Then this is the reward plus the max of all the old rewards, and then this is the new Q value. And some of you are looking a little bit with eyes like this. This is kind of difficult to imagine, right? It's a little bit fuzzy. Where am I talking about exactly? That's, I think, understandable. We could do it like this, but this works for a deterministic system, so a system which always behaves exactly the same. But for instance, if there's some kind of a chance involved, for instance, if you're playing with somebody else, with another player, or you have something, some noise in your environment, then you maybe don't want to trust too much on your latest judgment. Maybe you want to take a little bit more of your history, and a little bit less of maybe that one chance factor. So we could do it like this. So then we take the old stuff and we take into account the new stuff, but with a factor. So let's say we take 90% of the old state and 10% of the new state with a learning rate. Yeah? I'm not going to go too much on because this is already quite theoretical, I think, right? And there's another thing. If you take, for instance, in the beginning, let's say you take a move like this, and you take a move like this, and here you explored these 3 moves, and they're all dog moves. You're really bad, and you go here and you go, oh, that's really good, and this one's really good, and this one's really good, and basically this algorithm you will end up only exploring this tree, right? But there is here also one golden opportunity which you didn't do because after some time you found out, well, this is really bad, low max Q value, the future max Q value, I'm just going to explore this one, but you missed this one. So sometimes you just want to do a stupid move and see if you missed something. And that's the idea of this thing, and you could use the greedy method. So most of the time you pick, for instance, the best move, but sometimes you pick a stupid move. You do that randomly. Because the problem is the real system you cannot explore totally, right? It's just impossible. You cannot explore all the different things in reality, what's it going to be. So you need some stuff to guess the performance of the real system. And that's true for chess, that's true for Go, but it's also true for somebody walking. It's too complicated to have the whole exploration of everything the system can do.
But it's near to random forest, yeah? In concept.
Try different things and see which is good and which is bad.
Yeah.
Yeah. Well, the whole idea that you take different possible moves looks a little bit like a random forest. But this is all input for, in the end, or all the time, training your network. To train, this is all stuff to train this part.
I think the difference here could be by the prediction, because by the random forest we have all the data and we have the prediction, but by this we are making predictions to use.
Yeah, and we're updating the predictions all the time, and because then the system gets better, and then we update the network again. So it's really iterative, and that's also why it takes much more time. Yeah, I really think only on this subject you could teach for several weeks. Yeah.
Sure.
Yeah. We're not going to do that. I think we don't have labels, we don't know the correct input. Getting the labels depends on the system. And for tic-tac-toe, that's much more easier than for chess, right? For tic-tac-toe, you can basically play the whole game, all the possible moves, and then you can reinforcement label. For Go, it's more difficult. The labels don't stay fixed, eh? As you play, you get better, and then the labels change. So you're constantly playing around. It is tricky when you look at how often it doesn't work, and also I played around with it, how often it doesn't work. It's really much more difficult than the other stuff, but it is a very promising field. And it works a lot, this is what I said in the beginning, it works a lot like a baby growing up. And you see already that's a much more difficult process than just learning for an exam. Also, if you would now try to learn, well, I've got some examples. I've squashed all my life, and I took one lesson of 1 hour with a serious squash teacher, and my level went from this to this. So what did I do normally? Normally I did unsupervised learning. I'm just trying to see what happens, right? Like, and that's also how I do, like when I play squash. I do, and that 1 hour was supervised learning. And it goes much quicker. He was clearly going, no, you have to take your hand a little bit like this. Ah, okay. And it's shocking, the difference. Okay. Questions? I do think this is, from an engineering point of view, really interesting. Because I think this is the goal of, no, not the goal, but the roadmap to having really natural robots who walk around and all that stuff. I could also show you some videos of Boston Dynamics. They don't only do reinforcement learning, but they also apply it. Did you see in the open dock, did you see the robot spot walking around 2 weeks ago? It was really impressive. Okay. How am I time-wise? 40 minutes already?
Yeah, almost.
Okay.
35, yeah.
Okay. Image recognition. It's not something we really used a lot. Well, it's used a lot. A lot of it is what Johan indicated with the CNN. And I think this is really a huge field, and it will only grow bigger. I think this is basically the future. But there are lots of other methods, and I just want to show you one method which I think is really nifty, really smart, and it also touches basically the same concepts as data science, and I'll explain. So it's I'm going to explain face recognition. Face recognition was notoriously difficult, and there was a breakthrough with this algorithm, which I'm going to explain. And it was really difficult because we had methods, but they were too slow. And at one point, and you don't know anymore because I think you were still 10 or something, but at one point it became available on phones and cameras. And it was really like, ooh, this is hip. And it was all this algorithm. This made it possible. And I don't, face recognition, I have to disclaim it, this is not recognizing the face, but recognizing a face. So it's not that it's Peter or Thomas or not, but it's really like, oh no, there's a face. And what we're going to discuss is hair detection, Viola Jones. Oh, you were not 10, you were even much younger at the time. But this is the first paper where they proposed this technique. And it's not it's not hair, but it's a type of feature. So it's the English hair. And it uses weak classifiers. And you've been working with weak classifiers all the time. It's fast by using smart tricks. This is the idea of a weak classifier, and I think when we talk with the recipe group, they probably know what I'm hinting at. If I put a new data point in it, what is it? Is it EQ3 or EQ4?
Hard to tell.
No clue, eh? No clue. It's no clue. You've got no idea. And the idea of reclassify is that if you put in a lot of data, then we maybe can say, well, it's probably more EQ4 or EQ3. If I put a lot of points here like this, what do you think it is probably? It's probably EQ4, yeah. If I've got a lot of points like here, well, maybe it's 3. So that's the idea. So the estimated value of that feature is really bad. It's totally useless. So it's like 51% versus pure chance 50%. Not useful. But you can do stuff. The classifier it uses is it chops up an image in different areas and it looks at if is it darker or lighter. If this is darker than this, it's for instance 1. If it's lighter, then it's -1. So it takes the average of these values, in gray value, and then it just says which of the two is bigger. Yeah. If the difference is bigger, by the way, you get a bigger signal. And we use these kind of classifiers, so it's not only 2 boxes, but maybe a little bit more. And in actuality, it's a lot more than this. A lot of these boxes. And what is the idea now? This is the idea. On average, it's probably true that this is probably a little bit darker than this. On average, it's probably true that this is a little bit darker than this. On average, probably true. And we do this for 6,000 features for the face of Thomas and for the face of Jason, etc. And for Thomas, it's like hit rate for 60% of that one, and for Jason it's for 67, also differently because Jason has a beard, so it looks different, blah blah blah. But there is some statistical, it's a little bit better than this, than the wall, because this one is also darker than this, right? Okay. And these are called Haag features. This is a really nice one because we've got a movie, and this is I really like this movie. Here you see real time, not real time because it's played out, etc. But you see the image scanned by the Haag features. What you see here, there's a couple of things. You see stages 1 to 11 stages. So sometimes it gets further in the stages, sometimes less. You see here a number of features per stage. You see a percentage of how good that stage is. Blah blah blah. It's all not really a face, right? Not really. Does this look fast?
No.
No, not really, yeah? Because you have to calculate for each piece the intensity, right? For each rectangle, so that's stupid. It's a stupid way to do it. Maybe. Now we're getting somewhere, almost. It takes a longer time, it reaches higher stages, 22. Yay. And it leaves a red rectangle. Apparently the process at this position, it went to the end. And if it went to the end, it says, well, it's a face. Yeah? I'm going to explain this a little bit. What's happening. So you've got different stages. And basically, for each stage, you will get more and more features. So the further you are, the longer or the more features you're trying. And basically the idea is that you cut off here or whatever, but you stop when you think, well, this is not promising enough. And if it's promising enough, you go to the end. And if you go to the end, then there's a face. And the success rate per stage doesn't have to be big, but the fact that all of this is statistically a little bit better than doing it on this means that it's a face. But it's a huge processing power, right? You need a lot of different stuff. Well, there's where the smart math trick came into play. This is huge. It's never going to work. We don't use the image, we use an integral image. What is an integral image? Instead of at each position the intensity of that pixel, at each position we've got the sum of all the pixels to the left. We have to do that one time for each image. It's a little bit of work, but not that much work. And now, if we want to have, for instance, the average value of this one, we just take this point, right? Sorry, this is the original. We take the value of this one and then we have to divide by 6 to have the average value. Right? Yeah, but if it's like this, it's more difficult. It's true. Then we have to take this, but then we have to subtract this one, we have to subtract this one and add this one. You can do some math and find out why. But you replace summing like 100 points, you replace it with just adding 4 numbers. And that's the math trick which makes it really quick. Because all the things you saw, every feature, it's actually just one summation. So that's usually fast. That's how it works. Yeah, this is the steps, stages, and it can break down and like, oh no, this is really not enough. Face like, oh, this is face. Okay. How much time do we have?
15.
15, okay. Still awake? The next thing we're going to do is natural language processing. I will finish basically on explaining the paper where ChatGPT is based on. So I will finish with a paper from 2017, I think. The paper is named "Attention is Everything."
Transformers.
Yeah, but the
Yep.
paper is named "Attention is Everything."
Right.
So that's what we're going to do. And I'm going to explain a little bit the evolution. I'm going to explain first the RNN. That's what Johan already did. ChatGPT doesn't use it, but it kind of gives already a little bit insight in the concepts. And what we're going to do here is just on a translator model. So English in, German out, French in, English out, stuff like that. And why it's interesting, because it's you need to encode the meaning of language to do a good translation. You need to encode really what do you really mean with the sentence, which is exactly what ChatGPT is doing like almost all the time. Yeah? So we're going to do RNN, beam search, attention model, and we're going to end here part of it. I've got a really nice movie you can watch offline, which is brilliant, I think. Okay. The first thing is a English to Spanish translation. This is an RNN. Do you remember what RNN was? Did you remember from
Recurrent.
Yeah, we had Johan said that it's the way you display it is different. Normally you've got this, like this, and an RNN you how did you like this, And what was the idea? Because you could place them next to each other, right? And then you had some kind of an error in between, something like this, you remember? And what was this?
Timestamp.
Yeah, it's timestamp. It's actually the same model, but a little bit later in time. And I'll talk a little bit also why ChatGPT doesn't use this anymore. Well, spoiler alert. Can you parallelize this nicely? Can you put this nicely in an FPGA, like parallel processing, if you have a time step? No, it's difficult because you've got, and ChatGPT uses a model where you can do the things separately from each other. So you can use, so it's really a computational power driven change. So here we have our sentence. And what I'm showing you is the training phase. So not how it works, I'll show a little bit later, but the training phase. And we know, I like soccer, we know that the output is me gusta el fútbol. And we've got an encoder network and we've got a decoder network. And again, this is just the same network, different points in time, right? And you've got this network and you've got this network. You translate the words to numbers, and then you do trick embedding. I'm going to explain embedding a little bit later. You're going to feed this into this network, and the output, basically the same as Johan already explained last time, is done here. And there's a trick here. Start with SOS. Do you know what SOS is? Very stupid. Start of sentence. So the trick is here that you, in the training, you start with an empty thing, and what you want out of it is me. Yeah? So later on, if you want to use this network, you don't have this sentence, right? But you do have the SOS. And then it can give me, and then you can translate me to here, and then you can do the next one. Right? It's a little bit, you still see it a little bit back in GPT. It gets really word for word, right? And that's not a trick, that's really what's happening. And not because of this, but because of some other stuff. But it's really based on what it did before, and then it looks at the next word. Softmax activation, you remember what it was? Johan also addressed it already.
It was like one output or something, right?
Yeah, you normalize it there and you look at the chances. I'm doing it correct, eh?
Yeah, sure.
Yeah. So the chances summarized is 1, but and you also make sure that the one which was the best is a little bit stronger than the other one. Yeah, sure. So basically you start by training it by this. So what you apply is this. Apply the SOS, and what you want out of it is me. So you've got the label. So you're basically supervised learning. I'm going to explain first a little bit about input embedding, and there's 2 things about it. If you've got a word, hello, computer doesn't understand words, right? So translate it all to vectors. Now why do you think that not just a simple number? It's possible also. It's actually a too difficult question. I'm going to explain a little bit. So basically, and now this is a 2-dimensional, but this is actually a multiple-dimensional space. We translate each word to a number of vectors. Or not to a number of vectors, to a vector with different numbers. Right? So if you would have just 2 axes, then here you've got dog, cat, and you see already here some clustering. Right? That's done on purpose. This is all in the training phase. And there's a nasty thing here, and I'm going to explain a little bit later also. Dog is not always the same, right? You've got a nice dog. Your face looks like a dog. It's a different dog, right? It's a different meaning of the word. I love my wife. Yeah, okay. I love peanut butter. It's really a different word, actually. And it gets also a different vector in this space. And that's already really a strong concept, because it means you're understanding the word better, right? Where does it depend on, the function of that word? Yeah, the context of the sentence. Yeah. Okay. So basically, if we train it, we just put in SOS, then it gets out me. Then the me we put in back in here. Then we get encounter. This was wrong, by the way, but okay. Then we put that here, etc., etc., etc. So this is how you use it. Yeah. There's some difficulties with this. What I just told you, it's after each other, so you cannot parallelize it very nicely. And the other one, and the thing they've tried to fix it with, you can take the wrong turn, and then you end up in the wrong thing, because what you saw here, if this is encounter, then encounter comes here also, right? So then the sentence can go totally the wrong direction.
Yeah, so how does it know what, so L is like a head of the lidwoord?
Yeah?
So does it looks like it should make a mistake, it could easily make a mistake,
Yeah, yeah.
and then you're done.
Yeah, yeah. Now, what one way to solve it is beam search, and then you don't go one path, but for each word you try the best 3 contenders. And then you're a little bit back to the reinforcement problem, because it could be that your move is not so good, but then really good moves come, and oh, actually this sentence is better. So that's one way out. This one way to fix it. But apparently there was a bit better way to fix it, and what they did is attention. And when we look at this sentence, if you read it, your mind is probably doing something like this. With great power comes great responsibility. You're focused not in one time the sentence, but it goes a little bit like this, right? But there's something interesting. With great power comes great horsepower. That means that your power changes, right? So where does this power have the most relation to in this sentence? Which is, to understand the word power, what is the most important other word?
Responsibility.
I think responsibility. Yeah. So we'll come to that. That's also something, hey, this is interesting. It's not going to come into this one, it's going to come in the end one, in the attention transformer model. This is where they try to do this attention thing in the RNN. The problem with the RNN, and Johan also explained it already, it forgets, because you always get input from, you only use the last output, it forgets the first word, right? I like soccer, and when you're close to translating soccer, you forgot that somebody said I. So that's how RNN works, because you're always getting a little bit of the first input. So a way to fix this was with the attention mechanism. So the encoded value, you remember this was in between these values. You put in a separate piece of program, and you train this one also, and you use that information also. So it could be that this actually is important for I, is important for man, for instance. And the idea was then to, this one, to use that to not only give the oldest outcome, but also a little bit of the previous one, mixed with this weight. So in case of with great power comes great responsibility, when you're translating responsibility, you're probably looking at the word power, or vice versa. Yeah? Quite difficult concepts, but the other one which is possible is what Johan also explained the last time. LSTM networks, you remember? The long-term, short-term memory stuff. You could use that also. Okay. In 2017, somebody thought, well, what if we try to use parallel computers better? So can we translate this mechanism to parallel computers? So FPGAs, your video card, that's all parallel computing. It's much quicker. And he made the attention model. So this is the basic, what I just explained. So you've got T, and it comes something out. Red, dog, could we do it? Do a dog, boom, like this, and then we can give different parts of the computer different parts of this. That's the idea. Try to do parallelization. And the idea which came out of it is this one, and I'm going to not explain everything, and then I'm finished, but I'm going to explain, I think, a little bit until here. And explaining is a broad term, it's like giving a feeling of it. Okay, input embedding. So that's the first step. AJ dog is beauty, AJ looks like a dog. Different meanings, right? And it should actually mean that you come out with a different factor, right? So how do we do this? This is dependent on the place in the sentence. So what we do, we're going to look at the other words and then tie that into the meaning of that word. So we're going to do a positional encoder. So we're going to use the position of that word into the sentence. So it could mean that it means a nice dog, it could mean ugly face. And it depends if the other words in the sentence and the position of that word. So then we're really going into insight, right? That factor space is not just English word anymore, but it's a concept also. And you can understand already that ChatGPT really looks at concepts, right? It doesn't look just at words, it looks at concepts. Okay. Then, after this thing, we're going to look at this one, the multi-head attention. And the idea is that where does D belong to? When I want to translate D, to what word do I need to look in the sentence to know the context of the word D? Well, it isn't about the big, it's not about the red, it's about the dog. What you see here is that, well, the attention when you look at D should go to D, okay. But also to the dog. It's the highest after that. The big, you shouldn't look at red, you should look at dog. Big, dog, these two are the highest. So here you're really encoding words and sentences in their meaning. And this is the big idea which made ChatGPT possible actually. To encode things like this, in this way.
So the factors are a result of where the words were positioned before in that.
Yeah.
But then who or how were those positioned and placed in that huge
Training.
Oh, that's all by training.
Yeah, the ChatGPT, when you use it, it's a huge database. It's a huge. They used a long time to train it. And also it's a little bit before that, but the sentiment analysis is also nice. But
Right.
IMDb, there's a label which indicates if it's a good, a positive review or a negative review. With that you can also use to train, and it's too little data set to really, but it's already an indication of it. But this is basically all the human knowledge which it trained it. But this is also what happens when you were a child and learned to read and write and speak, right? You learned, hey, this has different meanings, these words, depending on where they are. And basically what it then happens is just a normal neural network. This is the encoder part. And, then it's feed. This is the, so basically it's just a normal neural network. Because you need to translate it, because this was still a language translation. Let's see the total one. This was a language translation. So well, basically, if you've got the concept of words, that should be the same more or less in each language, right? Sort of. I'm talking about a house and a specific like this and this and this. Oh, in French I would say it's like this. And it could be that in French it's actually two things, so that in French it's two, but okay, but then it means this one splits also, oh, the house, well. But basically it's, again, a standard classification process. And of course you have to do that in the same space, right, when you learn it. You have to make that translation for English to concepts, but also for French for concepts. And then you do this here for French, here for English, and here you start making the French sentence. So this is how you train them. Because here it's again the same thing, with the outputs shifted right, remember, with the SOS starting, it's the same concept. But this thing you can do in parallel. this thing you can do. Okay. And this is the scratching the surface of ChatGPT. Basically, this is what started that revolution. And there's still a lot more to tell about this. For instance, ChatGPT also use human operators to train it. So they really had human operators to label data. And label, well, not data, but label how good the network was performing. So that's basically another reinforcement learning step, right? You need a different process to say if it's good or not. So it's more complicated than this, but this is the basis. And that's it. How am I time-wise?
Yeah.
Oh, okay. Still 23 minutes. Is it clear? Interesting? I think it's hugely interesting. It's really cool.
So all of these basics are also in the hands-on machine learning book,
Yeah,
right?
it's super. The book
So-
is really...
So if you really want to dive into this stuff, then work through the book and.
Yeah, although I did, for instance, for this one, I used, I started with the book, but I transferred, because this part I thought in the book was a little
Right.
difficult explained,
Mhm.
and then I transferred to this one,
Right.
and this was like, wow. So I would also try to use tutorials. I'll put this one also in the